The hockey shot has many components, starting from using the right twig, to the wind-up of the shot, to the release. You have to have everything done correctly. For the purposes of this video, the conditions for the shots that I will be talking about will be in an ice hockey scenario. Let's begin.
And he puts it right under the bar. Good luck stopping that. Wow.
Before the shot is even taken, there are a few things to be aware of in regards to the stick. The hockey stick is designed to enable good puck control while also being lightweight and able to withstand the forces applied upon it. There are a few key features of the stick that really affect how well a slap shot will go. The first one being the curvature of the blade. The curvature of the blade acts as a self-centering mechanism for the puck. The curve forces the puck to the bottom of the blade upon impact. In the NHL, there is a rule pertaining to the stick blade, which is as follows. The curvature of the blade shall be restricted so that the distance of a perpendicular line measured from the blade shall not exceed 3/4 of an inch. The curve on the blade helps the puck to spin. This enhances the stability during the flight, similar to how a frisbee works. This, along with the self-centering properties of the blade, allow the shooter to aim the shot where they'd like it to go. The second feature that affects the shot is the face or loft on the blade. This can be described as the tilt or openness of the blade when viewing from above. The tilt aids with the elevation of the puck. The initial angle of velocity is also affected depending on this same tilt. The third component is the angle of the lie. This is the angle between the blade and the shaft. This angle pertains to the skating stance of the player, depending on if it is more upright or more crouched. This will affect how much the blade will be on the ice. As the player begins to swing, they raise their stick. When this happens, there is potential energy as the stick comes up from the ice, and kinetic energy as the player moves their arms in a swinging motion. As gravitational potential energy decreases and the stick moves towards the ice, something interesting happens. Before hitting the puck, the blade makes contact with the ice first. The coefficient of friction between the blade and the ice is at an almost perfect level because the mu allows the stick to maintain the majority of its forward motion while beginning to create an elastic potential energy buildup in the flex of the stick. This is caused by the friction pushing back against the stick. The elastic potential energy stored in the stick is used to apply a force onto the puck. In this diagram, we see a hockey stick is clamped at the butt end. A force represented by F, which is the force pushing back against the blade, is applied. The blade moves through a distance which we will call x. Since the force is proportional to the distance traveled, we can set up a statement F equals k times x, with k being the spring constant, or in this case, the flex of the stick. If the stick has a high flex, then we know that k will be large. However, it is typically about 1,000 newtons per meter, which we will use for our example as well. Therefore, if the stick travels 0.2 meters, and the flex, or k value, is approximately 1,000 newtons per meter, the force will be 200 newtons. Here are some more examples of sticks. You can see that as the flex changes from wood to carbon fiber, the k value varies as well. If you place a puck on the blade and suddenly decrease F to 0 by lifting the blade in the direction perpendicular to the motion of the puck, you will have a shot in the air and the stick will vibrate. Furthermore, to add on to the energy used throughout the process, since we know that the law of conservation of energy states that energy cannot be created nor destroyed, the elastic potential energy at the beginning is converted. Upon hitting the puck, the stick creates kinetic energy pushing the puck forward. However, there will also be some energy that is heat and sound energy which is released. When looking at a shot, it's easy to see that it's very powerful. However, in science, especially in physics, we say that power is the amount of work done over time. Therefore, the quicker you can get off the shot, the more powerful it will be. The new technology being created in the realm of hockey sticks is to increase the control the player has of the puck and the force they're able to generate from the shot. The hockey stick has seen many advancements, at least over the past 30 years. In 1995, the first composite blade was created. Paul Kariya was one of the early adopters of this type of blade, and he scored 50 goals with the new technology. By 2004, approximately 90% of players were using composite sticks. Since then, composite sticks have swept through all of hockey, and now it is the exception if a player uses a wood stick. However, the advancements have not stopped at the transitioning of material. Over the past years, a company called Tovi has been taking strides in an attempt to create never-before-seen stick design. Tovi is a relatively new company that has created a blade with holes. The weight of the blade is approximately 400 grams, which is slightly more than a standard composite blade. This is due to the fact that they do not need tape for this type of blade, and it does not have a foam core, as a regular composite stick such as a Bauer would have. According to Tovi, the Diamond Air blade's aerodynamic design allows the swing speed to be increased to 13% faster for the same physical efforts compared to conventional sticks. This would be due to less air friction upon the slap shot. This translates into increased shot velocity according to Tovi. The Diamond Air blade has also been manufactured with micro-grip surface texture and is treated with their patented Diamond Coat liquid tape. These are supposed to allow for better grip. Before I made my decision in regards to the technology of Tovi, I wanted to make sure I had all the facts. So I sent them a quick email and just told them I was doing a physics project and had a few questions. You can see here the response they gave me. It was detailed and provided me with some good information in regards to the stick. The total carbon fiber blade doesn't necessarily make the stick more durable, because you need a slight amount of give from the blade in order for it to be able to withstand the force. That's what makes a material like a foam core blade so good, because it's able to withstand these high amounts of force. The stick would not be able to help with stick handling, because if you've ever stick handled blade with no tape on it, you'll know that there is not as much friction created between the ice and the blade. You need a certain amount of mu in order for this balance to be able to be created. And this would not be the case if you use the Tovi blade without tape. However, it would help to be more aerodynamic. There's no doubt about that, because if you have the holes, then more air will be able to pass through and not as much will be pushing back against the stick. So this inevitably would help. As well, the blade does offer more support. When you shoot, the energy is transferred from your body, like I've mentioned, through the stick and down to the blade. The diamond pattern of small triangles would increase the stability, similar to how support beams do in a building or on a bridge. So for these reasons, there are benefits to the technology. However, I would say that overall, at the price point that has been given for Tovi, which is about $200 as the starting price for the stick, this investment is not worthwhile. The technologies that are currently being used in Bauer, CCM, and other brands do work, and they do have high levels of success. So until Tovi is able to develop their technology a bit further and able to bring down their price point, I don't think that Tovi is for me. That concludes this video. To recap, I talked about the hockey stick and the hockey slap shot and the forces acting upon them. Thank you for watching.